Whiteboard Physics A-Level Lesson 75, Everyday Physics Instruments. Yes, there are lots of everyday instruments. The ones we're going to talk about at the moment are things to measure lengths, maybe things to measure times and masses as well, if we get time towards the end. So let's talk about measuring lengths. Very often we're interested in measuring heights. And if we're interested in measuring heights, then we need to make sure that the ruler must be, let's write that so it's a bit more legible, must be vertical. And how do you check the ruler is vertical? There are a couple of ways, 3 ways. Vertical. So method number 1 to check that a ruler is vertical is to use a plumb line. You take your ruler like this. Let's just label that ruler. And then you drop next to it a plumb line. Now, what a plumb line is a vertical, it's just a piece of string which will hang vertically because you place a mass on the bottom. The mass is called a bob or a plumb bob. Like this. So the plumb line will hang vertically. This is your bob at the bottom. And what you do is you adjust the position of the ruler, which will be clamped in place. Clamped in place. I won't bother drawing the clamps. You adjust the position of the ruler until it's vertical using the plumb line to help you with that. That's the first method. The second method is to make use of a horizontal platform. So you place your ruler on a table, and you know the table must be horizontal. So let's just label this ruler. Once again, it's clamped. This is horizontal surface. Horizontal surface. And then you use set squares. And you use 2 set squares. We use 2 set squares, not just 1. So let's label these set squares. They're triangular-shaped things. 2 set squares. And they should be in 2 different orientations. So when looking from above, they should be 90 degrees. 90 degrees from above. So that there's one along this side here and one along the side there. And as long as they're pushed up properly, the set squares have a 90-degree angle at the bottom. As long as they're pushed up against the ruler will be perpendicular to, or orthogonal to, the horizontal surface. Of course, then we're relying on the surface actually being horizontal, and so there's an assumption that's made there. The third method, which I think is the cheap method, because, well, not all schools can do this, is you use a spirit level. Well, you use 2 spirit levels. Spirit levels have a usually they have a bubble in it, so sometimes they're called bubble levels. A little bubble in it which moves within a window, and that gives you information about whether or not the level is level. It wouldn't be that level we're interested in, of course. It would be the bubble that's on this direction that would be interested in, the horizontal direction. So let's label that 2 spirit levels. Spirit, that's not quite, it says spint, so joined up handwriting. Spirit levels, and they are once again 90 degrees from above. And this is our clamped ruler. So there we are, that's the first thing. Make sure that your ruler is vertical if you are making measurements of height or anything else where it's a vertical measurement. We could also try and insist if we're making horizontal measurements that things are horizontal. Now, to make sure that things are horizontal when we want them to be horizontal, we can get rulers that are properly vertical and measure different points along it. So measuring horizontal lengths. For example, we might be doing Young's modulus measurement. So what we do here is we have the thing we're measuring with, which is the ruler, clamped in place. Here's our horizontal surface. Here's the ruler. And then we would measure with another ruler, which is vertical, in two places, two opposite ends. And we make sure that ruler is vertical using one of the above methods. So let's just label this vertical ruler. This is also a vertical ruler. And this is a horizontal ruler. And this is a horizontal surface. And we just ensure both ends of horizontal ruler are at same height. There we go. And that is, move that up a little bit, that is how we measure horizontal lengths. So, you know, this is, I think, quite common sense stuff, but when you're doing practicals at A level, it's important to get the little details right. Right, verniers and micrometers, vernier calipers and micrometers. I don't know how I'm going to translate how to read them properly onto a set of notes like this. So I might just make a note here. We'll start with micrometers. And I'll do my best at a dodgy sketch of a micrometer. So for a micrometer, you've got your the part like this, which goes like this. And then you've got the anvil there. You've got the spindle that goes through here. Then you've got the sort of the main scale coming out here. And then you've got the bit that screws there. And that's usually got some sort of grip on it. So maybe a bunch of dots or something to grip. And then there'll be a bit that comes out the end as well. So this will have, let's use a different color for the scale. This will have a scale on it. And then this will also have a scale on it, like this. Okay, so the first things first, the number on the scale should match the size of the gap. And it's the gap between the spindle, which is this bit, spindle, and the anvil, which is this bit, anvil. Right, so each time we rotate the, what do we call that bit? The barrel, I guess? Let's label this bit the barrel. Barrel, how many R's in barrel? Probably 2. Barrel. Every time you rotate the barrel one full turn, so let's use red, when when barrel rotated 360 degrees, let's say, one full turn. Let's write one full turn. One full turn. The gap, and I'm going to call this bit here the gap, increases 1.00 millimeters. That's what it does. And you can read that because the edge of the barrel lines up with what I usually call this the main scale, which is on the stem. Main scale. So you can read that off the main scale. But of course, you can rotate it less than one full turn, and thus open the gap less than one full turn. In fact, I've made a mistake here. Sorry, it doesn't increase 1 millimeter, it's 0.5 millimeter on the ones that I use. It could even be 1/4 millimeter on some of them. There are different designs, but the ones I use at school use 0.5 millimeter. And so on the main scale, it has 0.5 millimeter resolution. So as the gap opens up, the edge of the barrel moves past the main scale. But then there are 50 marks on the barrel. And you line up which mark lines up with the line through the main scale, and that is the number of hundredths of a millimeter. So read hundredths of millimeter from barrel, where it lines up with the main scale. And I'll leave it there because unless you get your hands on it and practice this, you're not going to be able to learn how to use it from a written description. You've got to get these things in your hands. So vernier calipers can be spelt with one L or two. I flip-flop between the two spelling. Vernier calipers, we have a part that doesn't move. Which way around should I draw it? Let's draw it this way around. We've got a part that doesn't move, and it's got some sort of quite interesting shape usually. There'll be a bit that comes up like that as well. And let's just rub out part of this because it's gone too high. It goes along like this. There's a part that doesn't move, and then there's a part that does move. So we've got sort of this sort of shape. And then it goes like this, and then it goes down like this, and then it goes like this. Then we've got this kind of other side of the jaw. Gone too far. Let's do the other side of the jaw here. Let's do that coming up like that. Like that. And then the rest of this is just the bottom bit there, which goes like this. And then usually the bit that slides is attached to a needle that comes out as well. And this is good because you can use this bottom part to measure depth. Measure depth. You can use this part, these two, to measure interior diameter. Put the word measure interior diameter. And you can use this part here to measure exterior diameter. It's a very versatile instrument indeed. Now there's the main scale that runs along this instrument, like this. Main scale. And there's a window. In the part that moves, the sliding part, there's a window. And when you look through this window, you can see the main scale. But it's right up against the edge of the window. So that's not very well drawn. But it's right up against the edge of the window. Let's see if I can do a better job. There we go. And I'll use a straight line tool for this. Nice. Just like that. Now on the slidey part, there's another scale, and there's a notch, which is labeled 0. And when the jaws are fully closed, then this 0 notch lines up with 0, and you know that the length is 0. I mean, there'll actually be a bit of an edge like that to it because of where these scales are. But anyway, it doesn't matter. When it lines up, the jaw is 0. Put that a bit too much, I reckon. Up there. Yeah, the edge, the gap will be 0. It should be 0. But then you've also got these notches on here, which is called the vernier scale. And there are usually 9 of these vernier notches that fit into the space of 10 on the main scale. So this is the main scale. This is the vernier scale. So your first task is to determine where 0 on vernier has passed on main scale. Because if you passed it, you've got more than that millimeters in the gap between the jaws of the caliper. And then you see which vernier, which is 0.1 millimeter, lines up with, and it doesn't matter what the number is on the main scale, but lines up with a main scale line. So if the third one lines up, that's 0.3 millimeters more. If the fifth one lines up, that's 0.5 millimeters more. If the 10th one lines up, you're actually on the next millimeter. But again, you can't learn how to read a vernier scale, just like a micrometer scale, from some sort of theory lesson. It's not going to work. You need to get these things in your hands. Right, now we've got a little bit of space at the bottom to talk about timers. So when timing oscillations, have the oscillations already happening. So don't start from the first oscillation. Don't start from first oscillation, because then you're trying to react to it, and there's an extra uncertainty from your reaction time. Oscillation. And then when you do start oscillating, start counting from 0. From 0, and do at least 10 oscillations. 40 would be better. So at least 10 oscillations. 40 is better, or more. There's no point repeating any timing measurements where you're timing oscillations. There's no point repeating it, because you are essentially doing 10 or maybe 40 repeats as part of the investigation. And lastly, balancers for measuring masses. Make sure they're zeroed at the start. We call that 𝗟. So ensure zeroed. Ensure zeroed at start, and ensure level. They sometimes have little spirit levels on them to make sure they're level. Just like that. So lever balancers, or triple beam balancers with a big lever, they tend to be more accurate than the spring balancers. Electric balancers are usually the best in terms of resolution. And the best thing about these balancers is you can zero the digital balancers very easily at the start. Any instrument that you can zero at the start, the uncertainty in a reading is actually half of the resolution of the instrument. Because there's no uncertainty in the 0 value, because you've set it at 0 by pressing that button. Whereas with analog instruments where you can't do that, the uncertainty in a reading will be, in a single reading, the uncertainty will be the resolution of the instrument. Right, and I will stop there. So that is basic instruments, how to use them, kind of roughly. Next lesson we'll talk a little bit about evaluation and analyses, and then we are done with this topic about practical, well, we're nearly done with this topic about practical work.